Hello and welcome to today's lecture. So, in last class we had discussed about expectation variance and covariance and seen how you can use various functions or transformations to calculate expectation of Gx or expectation of summation xi, and same for the variance and covariance. Okay. So, today we will introduce one more concept to calculate expectation and variance of a population, and that is using moment generating functions. Okay. So, what are moment generating functions? Moment generating, okay. So, a moment generating function phi of t is defined as expectation of e to the power t of x. Okay. So, this would be summation e to the power t of x into p of x for discrete R v, okay, or okay. So, phi of t. Okay. Now, let us take the case of the continuous random variable, okay, and derive. So, if I do phi prime of t, which is d phi of dt, so then I can write this equation x e to the power tx f of x dx. Why? Because this entire function is a function of x except for this e to the power tx. So, when you take a derivative with respect to t, only need to take a derivative of this component e to the power tx. Okay. So, what do we get as a consequence of that? So, I can write phi prime of 0, okay, phi prime of 0, okay, is equal to minus infinity to infinity x f of x dx, which is nothing but expectation of x. Okay. Okay. So, I can write phi prime double prime of t is equal to x square. Okay. So, then if I put substitute t equal to 0, I get phi prime double prime of 0 is equal to minus infinity to infinity x square f x dx. What is this? This is nothing but expectation of x square. So, if I continue like this, I will get nth derivative of 0 is e of x to the power n. Okay. So, using these moment generating functions, we can calculate expectation or variance of a population in the generic case. So, let us solve an example to test it. So, imagine you have a probability density function f x. So, this is an example, okay, which is given by e to the power minus x for x greater than 0. Okay. I want to calculate the mean or expectation and variance, okay, of this population. So, what do? I start with phi of t, it is expectation of e to the power t of x, okay, equal to okay, okay. Okay. So, this I can simplify. Okay. So, let me do it on the next page. So, I have gotten phi of t okay, I can write this minus of x equal to 0, I have 1 by t minus 1, okay, equal to 1 by 1 minus t. Okay. So, phi of t becomes 1 by 1 minus of t. Okay. What is phi prime of t? Is equal to, okay. So, I can write minus 1 by t minus 1. Okay. Okay. So, phi prime of t is nothing but t minus 1 whole square. So, phi prime of 0 will give you 1 is equal to expectation of x. Okay. So, I can accordingly find phi double prime of t, which is equal to minus 2 by t minus 1 whole cubed. Okay. So, phi double prime of 0 equal to minus is equal to 2. Okay. This will return me a value of 2. So, I can then calculate, okay, I can then calculate, okay. So, I have calculated e of x equal to 1, e of x square equal to 2. So, variance of x is e of x square minus e x whole square is nothing but 1. Okay. So, this is how you can see that you can really make use of moment generating functions to calculate expectation and variance and so on and so forth. Okay. So, that brings our discussion on expectation and variance to a close, and we begin by discussing some special random variables. Okay. So, today we begin by discussing the Bernoulli So, let us take a coin toss example. Okay. So, here, okay. So, your outcomes are either head or tail. Okay. You can call your head as a success and tail as a failure. Okay. So, for an unbiased coin, okay, P is the probability of success. P is defined as the probability of success, and Q is probability of failure, is equal to 1 minus P. Okay. So, this is a single trial. Now, imagine, so this is just one particular example. So, if your coin is unbiased, then P and Q may not be half. If your coin is unbiased, then P and Q will be equal to half, but if it is biased, then P and Q may not be half. Okay. So, in general, so in each trial, okay, you call the outcome is either a success or a failure, depending on how you define an event as a success or a failure. Okay. So, now imagine you keep repeating the same trial n times independent. Okay. So, the outcome of one trial does not influence the outcome of the next trial, so on and so forth. Okay. So, for this random variable, okay, okay, we call x a binomial random variable, okay, with parameters. So, x measures the number of successes in n independent trials. Okay, with probability p. Okay, with parameters. So, x is called a binomial random variable with parameters n comma p. Okay. So, in this case we can have compute what is the probability of x is equal to I. Okay. That is, you want to have I successful events from n trials. Okay. So, that I events, so I is of course less or equal to n, okay, because n is the total number of trials. So, probability of x equal to I can be written as NCI p to the power I q to the power n minus I, okay, and with I can be anywhere between 0, 1, 2 up to n. Okay. So, this, since x is a discrete variable, this is my probability mass function. Okay. So, I can then calculate each of the probabilities. Now, in a single event, okay, in a single trial, let us say if I say x equal to 1 if success and 0 if failure. Okay. So, what is the expected value of x? Expected value of x is 1 into probability of success, which is p, plus 0 into probability of failure, which is q, is simply equal to p, which means, so this is for a single trial, right. So, for x, so we write x of I. So, x is nothing but x is summation of x of I. So, then expectation of x is going to give me p plus p plus p n times, that means equal to np. So, expectation of a binomial random variable with parameters n and p is np. Okay. 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 So, let us calculate the variance of x. Okay. Now, since xi are independent, okay, xi are independent. So, I can write variance of x is equal to summation of variance of xi. Okay. So, again we have xi 1 and 0, right, if success and if failure. So, E of xi square is equal to 1 square into p plus 0 square into q is equal to p. Okay. So, your variance of xi is going to be E of xi square minus E of xi whole square. This is p and this is p square. So, equal to, I can write p into 1 minus p, and 1 minus q is nothing but q. So, this is pq. So, variance of x then becomes pq plus pq plus pq n times. Okay. So, for a binomial random variable with parameters n and p, we have the variance as npq and the x and the mean as n times p. Okay. Let us solve a sample example. Okay. So, consider a company which manufactures discs. Okay. So, it packages 10 discs into one package, one pack. Okay. So, your probability, okay, of a disk being defective is equal to 0.01. Okay. Now, this company, okay, it has provides a money back guarantee if 2 or more are defective. Okay. So, the question is, first question is, what proportion of packages are defective? Second is, so if I buy 3 packages, what is the chance returning 1? Okay. So, what you see, you have pack size 10 disks in a pack. The probability of a disk, this is of probability of a single disk being defective is 0.01. So, when you ask, so let us try to solve the first question, first part of the question, what proportion of packs are defective? Okay. So, which means, or what proportions of packs are returned? Okay, is a question. Okay. So, now it is showing, this being a statement is, if there are 2 or more defective in a single pack, then the company offers a money back guarantee, which means that your package is returned. Okay. So, in order to calculate the proportion of packages returned, which means I want to calculate probability of x equal to 2 plus probability of, so if x is the random variable, which is the number of packages is defective. So, I have to compute probability of x equal to 3 plus probability of x equal to 4 plus so on and so forth, plus up to probability of x equal to 10, right. So, the probability p in our case is equal to 0.01. This is for a single. So, this is what you have to calculate, okay. But this is nothing but p minus okay. So, if x is the number of defective pieces, so this is what, for all these cases you have to return, okay. For these cases you do not have to return, okay. So, this is nothing but 1 minus probability of x equal to 0 and minus probability of x equal to 1, okay. So, this I can write as 1 minus, so from 10 C 0, 0.01 whole to the power 0, 0.99 whole to the power 10 minus 10 C 1 into 0.01 whole to the power 1, 0.99 whole to the power 9. Okay. So, if you do the calculation, you will see this will return you a value of roughly 0.005. So, this means that on an average 0.5%, so 0.5% of packages are returned. Okay. So, another thing you have to remember, that this p is the probability of a single disk being defective, which is 0.01, but this is the probability of the package being returned, which is 0.005. Okay. So, in order to answer the second part of the problem, that if I buy 3 packages, what is the chance of returning 1? Okay. So, I have calculated this probability, let us say probability of returning, which is 0.005. Okay. This case, so I am labeling it as p prime, because p prime is separate than p. Okay. So, what is the probability that I have to return 1 package from 3 packages? So, that probability is probability of y is the random variable that the package is returned. Okay. So, we need to calculate probability y equal to 1. So, total number of packages is 3. So, 3 C 1, okay, into 0.005 into 0.995. Okay. So, 995 whole square. Okay. So, this is how you do it. Okay. So, n equal to 3. So, n equal to 3 in this case at the package level, 1 is defective, you can have 3 different combinations, and then from here you have this is the probability of the package being defective, which you have a package being returned, which is 0.005, and then this is 1 minus 0.005. Okay. So, this will return you a value of 0.015. Okay. So, from 3 you have to return 1, the probability is nearly 1.5%. Okay. Let us take out another example. Okay. So, imagine you have a music system which comprises of n units. Okay. So, the probability of each unit working is equal to p. Okay. And this is independent. Okay. So, the probability of one unit working is independent of probability of another unit working. Okay. So, this is one. Other clause is the system works if at least half the units work. Okay. So, the system will work if at least half of the units work. The question is, what is the value of p such that a 5 component system works better than a 3 component system. Okay. So, you have n units, right, and we say, so there is a clause that the system works if at least half of the units work. Okay. So, for a 5 component system, so we want to find out the probability of 5 component system is greater or equal to probability of 3 component system. Okay. This is 8, 9. So, each unit operates with the probability of p, right. So, in a 5 component system, so for the 5 component system to work, it must at least have either, so from 5 you must have at least 3 components which are working, 4 components working, or 5 components working for the system to work. Okay. So, what is the probability? This probability is probability of x equal to 3 plus probability of x equal to 4 plus probability of x equal to 5. And we have this is greater than probability of y equal to 1 plus probability of y equal to 2. Okay. So, y equal to sorry at least half is working. Okay. Y equal to 3. Okay. So, for this I can write it as 5c3 square, this is this component, okay, which is this component, right. So, for a 3 component system to work, any 3 of the 5 can be chosen in 5c3 different ways. The order does not matter, it is just a combination. Say 5c3, p cubed is the probability of success of each component, and 1 minus p is the probability of failure of the 2 other components. Okay. So, this has to be greater than 3c2 okay. So, you can simplify this particular equation. You see you have at least p cube terms common across the board. So, you can rewrite this equation as 3 into p minus 1 whole square into 2 p minus 1 greater or equal to 0. Okay. So, p greater or equal to 1 is of course not possible. This implies that 2p minus 1 greater or equal to 0, implying p greater or equal to half. Okay. So, this is the answer. Your probability has to be greater or equal to half for a 5 component system to be more successful than a 3 component system. Okay. So, one last thing I will introduce today, so is how to compute binomial random variable. Okay. Compute means in a computer. Okay. So, you know that probability of x equal to I is equal to NCI p to the power I q to the power n minus I, okay, and probability of x equal to I plus 1 is equal to NCI plus 1 p to the power I plus 1 q to the power n minus I plus 1. Okay. So, I can take the ratio I plus 1 by probability of x equal to I NCI plus 1 by NCI p to the power I plus 1 by p to the power I q to the power n minus I plus 1 by q to the power n minus I. So, what is NCI? NCI you can factorial n by factorial I plus 1 factorial n minus I plus 1, this is factorial n factorial I factorial n minus I, this is p by q. So, I can simplify the following page. Okay. So, this becomes factorial I into p by q I plus 1 into p by q. Okay. Okay. So, this is a recursive formula. Okay. So, if you put I equal to 0, okay, so probability of x equal to 0 is NC 0 p to the power I q to the power n minus I, okay, okay, is simply n, okay, q to the power n. Okay. So, then you can use this expression to calculate x equal to 1. So, you substitute I is equal to 0 and then accordingly you get. Okay. So, this is how you can use recursion to compute these binomial probabilities in a computer. Okay. With that, I stop here today and we will continue with Poisson random variable in the next class. Thank you for your attention.